Now, it turns out that for most thermoresistors, the actual temperature coefficient of resistivity is not 1. They are something more like 0.004 ohms per degree C. Right. It turns out that the way thermoresistors are made, right, this value is rather small. And you can see the problem. If this value is rather small, you're going to see very small changes in resistance, and we're going to be more in this regime, right, than in this regime. All right. Thermoresistor, R sub T equals R sub 0 times 1 plus alpha T minus T sub 0. All right. So we talked about resistive temperature sensors, and I said there are some resistive temperature sensors called thermoresistors. Thermoresistors are characterized by being described by this equation, and their resistance changes by temperature, right? And this parameter is very clear. This temperature coefficient of resistivity is very critical to how much this resistance is going to shift. If this parameter is small, and it is, all right, then when the temperature changes, this is not going to move very much, all right? And that is problematic being our overall goal. There is something else called a thermoresistor. Being very careful here, right? Sorry. That's the same thing. Thermistor. Thermistor. Okay. Say it slow, you kind of end up back up here. Thermistors are also resistive temperature sensors. However, they're characterized by this equation. R sub T is equal to R sub 0 e to the beta 1 over T minus 1 over T sub 0. R sub 0 is the resistance at T sub 0, which was the same thing that we had for the thermoresistor, right? So again, just put a number here, okay? This could be 1 ohm, and this could be 25 degrees, right? It's a slightly more complicated equation, right? But just put numbers here. Beta is a material constant. It is also a number, and it can be on the scale of about 4,000, and R sub T is the resistance at temperature T. All right. Well, we have this sort of exponential here. In principle, these equations operate very similarly, right? We have a constant, constant, constant. Depending on the temperature, this temperature will produce a particular resistance. Just like this temperature will produce a typical resistance. However, if you were to plot a thermistor's behavior as a function of temperature, so here we have temperature, and here we have the resistance of the thermistor, it would look something like this. So as the temperature increases, right, 1 over temperature, right, as the temperature increases, this value decreases. Whereas before we saw an increase. Well, why are some things thermoresistors? Why are some things thermistors? And why do they come with different betas? And right, it doesn't have to be. Beta could be 4,000, it could be 3,000. Right, why are they different? I want you to remember that the resistors are physical objects. Right? There's a resistor here. A resistor is a physical object, right? It's made out of something, right? And we discussed how the resistance is a function of what it's made out of, right? Bigger resistors are not necessarily bigger. They just put something in here that has more resistance, more resistivity. We'll talk about that property. And so when you have a resistor that is sensitive to temperature, it is because when it heats up, its material properties change. And there's a whole bunch of materials out there whose material properties change with temperature. There are some materials out there that when you heat them up, their resistance goes up. And it actually goes up linearly. And when we make resistors out of those materials, we call them thermoresistors. Okay. There are other materials that when you heat them up, you change their properties in such a way that the resistance goes down. And when it goes down according to this relationship, we call them thermistors. Both thermoresistors and thermistors are resistive temperature sensors, right? They both have this function that as the temperature changes, they report it through their resistance. But they do so differently, right? And it turns out that we will be largely using thermistors. And the reason we will be using thermistors is they are more sensitive over the temperature ranges that we are interested in, which is basically physiological. There are thermoresistors, and they have different constants, and there are thermistors, and they also have different constants. But as a general rule, for the applications that we're going to be interested in, we're going to be using thermistors. Okay, so now you are given a thermistor. And let's say it has whatever values, right? We could say R0 maybe is, again, 1 ohm at 25 degrees C. Doesn't have to be, right? It could have been 10 ohm at 37 degrees C. This shouldn't bother you. These are just the constants that you plug into here. So you're given a thermistor and you're saying this is the way to go. All right. Now, of course, you can't look at a thermistor and know what its resistance is, right? So we need to put the thermistor into a circuit. We have a new problem, right? What circuit? It's the same circuit. It's the same circuit. Over the several weeks of this course, it's always going to be the same circuit. You're going to say, no, professor, it's not always going to be the same. Not always, almost always, it's going to be the same circuit. It's the voltage divider. And remember, in this class, the voltage divider is a means to an end. The voltage divider is our instrument. It's our tool. So we will take our thermistor and insert it here. Okay. What is the resulting equation for the circuit? It's the same equation. There's no reason why this equation would change. It's the same equation. And so as the thermistor changes its resistance, so will the voltage. So what do? Well, we go back to the situation where we know the battery, because we picked it, and we picked it well, right? We thought about it. We know the fixed resistance, right? And we have here, right, are unknowns, right? And this we measure, right? We build it, voltmeter, measure, right? No, 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 one unknown. So once again, we're in the same situation. If I built everything and I to use the same examples that the values we're very familiar with, if RF was 1 ohm and E was, well, let's change it just to change it. Let's make it 5 volts. E was 5 volts, all right? And we measure a V sub T of 2.5 volts. Then the question is, what is R sub T? Right? Well, I tried to keep it simple. So we have 2.5 volts is equal to R sub T over R sub T plus R sub F times 5 volts, right? And so we see once again, right, that to get, essentially we have 5 volts here, or we put 2 volts here, 2.5 here. We actually split it evenly. When a voltage divider takes the voltage and splits it evenly, it means that these resistances are the same, right? That's how we get a half here, right? So in this case, we would say that RT is also equal to 1 ohm. But of course, we don't want to know the resistance, right? We want to know the temperature. What is the temperature associated with 1 ohm? Well, we have to apply this. 1 ohm is here, right? This, in this case, would be 1 ohm. Beta is 4,000 from here, right? And T sub 0 is 25 degrees. So we have an equation, and there's only one unknown. So we can figure it out. It's a little bit more work than before, but it's not a problem, right? You can calculate it out, and you could figure out what T is. And so from this, you would be able to calculate what T is. Let's reiterate what we did. We measured the voltage. And then we back calculated through the equation for the circuit. And then we back calculated again using the equation for the sensor. And that's exactly what we did last time. It's what we're going to do every time. We have equations, and from a design perspective, it seems like it's moving forward, right? Pick the sensor and then put the sensor into the circuit, and that gives us this. But then when we measure the resulting voltage, we have to go backward, right? We take our knowledge about the circuit, right? Back calculate the resistance, and then take our knowledge about the resistance and back calculate the temperature. And that's how it works across all instruments. To conclude, this is correct. This is a good summary of how every medical instrument that measures works. All right? In addition to sort of getting into the examples of how you make a temperature sensing instrument, right? Well, let's start with that. How do you make a temperature sensitive instrument? Well, the sensor has to be sensitive to temperature. It starts and ends, in that sense, here. This is a temperature sensitive instrument only because we have a temperature sensor, right? Now it's inevitable. And now the process plays its way forward. We must connect the sensor to a circuit. The circuit, right, is reporting a voltage, right? That is the function of the circuit. It's reporting this voltage, right? Once we have that voltage, we can go ahead and figure out what the thing was that we were measuring all along, right? And we do that through this process of sort of working backward through the equation for the circuit and through the equation for the sensor. And you will see that that theme it's going to play itself out so many times in this course that it's going to become annoying how repetitive it is. And once you see it applies for one instrument, it applies for another, it's another, and now you'll see, oh, they all kind of work the same. Yes, they all kind of work the same.